Welcome. This is session 1-408, Understanding Windows 2000 and NT4 System and Process Activity. One announcement from the AV folks in the back: nobody can stand against the back wall or sit along the back wall because of cables that are run. So if you're standing against the back wall, please move to the sides, come down front. There are seats sprinkled throughout. Okay, nice to see everybody here. My name's Dave Solomon, and we're going to spend the next 75 minutes or so talking about kind of the basics on looking under the hood, what's running on your NT system. I'm going to start with a quick review of the tools I'm going to use. I'm going to go back and forth between my PowerPoint and a number of tools sprinkled throughout the presentation. Here's, just for your reference, a summary. Whoops. Coming up in a minute. Let me do my who am I? Who am I? Well, my work basically is centered around NT internals, studying it, writing about it, and speaking about it. Some of you may have seen my book. It's in the bookstore. How many people have my book? Okay. Hey, there's a lot of people who don't. I've been working with NT for about it'll be 7 years this summer, and as many of you know, NT and VMS share a close cultural heritage. I spent 10 years in the VMS development group at DEC, and so moving to look inside NT internals was like being at home again. So that's primarily what I do. Our company is in the exhibit hall, so I won't say much about what we do. We're a training company doing NT Windows CE classes. We're happy to have Mark Manassi working with us. Mark Manassi's in the audience somewhere. So the focus of this session is using tools to look at the basic internal behavior of an NT system, Windows 2000 or NT4. Most of this talk is applicable to both Windows 2000 and NT4. My assumptions for you is that you're basically 32-bit OS literate, that the term process or virtual memory or thread means something, although we'll have a brief review of that. In other words, we don't have any 16-bit PC weenies in the room. I have to just give thanks to my co-author of our NT internals class, Jamie Hanrahan, and also Microsoft NT Development, who has graciously allowed us to have access to the NT source code. So some of the information you're hearing in this talk was gleaned from reading sources. We are looking at Windows 2000 sources as well. But a lot of what you're going to see are things that you could observe using existing tools. Many of the experiments that I'm going to do in this talk are from my book. There's little experiment boxes, so if you're trying to scribble down details on the steps, you can take a look there. The tools I'm going to use: perfmon, of course, or what is it called in Windows 2000? Sys something? Sysmon. I'll be using the registry editor. I will be using the kernel debugger. We're going to talk about the kernel debugger at the end of the presentation on how you can use it to do a little bit of troubleshooting, especially on a hung system. And then a smattering of tools from the resource kit. Some of these tools are in the resource kit subset that is now included with both SP4 and also Windows 2000. So in the support directory, there is a subfolder called ResKit, if you haven't seen it before, on the Windows 2000 Beta 3 CD. And that's got, 50 or so of the 250 or 300 tools in the resource kit that are now shipped for free on the Windows 2000 CD. I don't have a delineation of which are in the free subset versus the full. I have the full resource kit installed on this laptop. I'm also going to use a few tools from a fairly famous or infamous website, sysinternals.com. How many people have visited that site? Almost all of you. Those of you who haven't should definitely go take a look there. Sysinternals.com is maintained by a friend of mine, Mark Rusinovich. Mark actually lives about 20 minutes from me in Connecticut. And Mark has developed some very interesting utilities based on reverse engineering. So Mark doesn't have access to the source code, but he's been slowly reverse engineering key pieces of NT over the last few years. And Mark's allowed to write about some things about NT I'm not allowed to say because of my access to the source code. So he's described some things in his website, some articles that he has there that describe undocumented behavior that I was not allowed to talk about in my book. So therefore I point people to that as another source for NT internals information. But the tools in particular fill some interesting gaps, even in the resource kit or some of the debugging tools that come with NT. So I'll be using a few of these. Some of these probably many of you have used. see some demos of those. My only caveat about these tools that I have to say to be fair to you is many of these include a driver. And the reason for that is they are reaching into system data structures to suck out contents of OS data structures that are not accessible to a user program. And the format of those structures, Mark has reverse engineered in many cases, which means that if something changes or he didn't get something quite right, that driver could get an access violation, and drivers that get access violations crash the system. Now, personally, I've only had one crash in using Mark's tools for 3 years, and that was user error on my part. So I've had no reliability problems, but just keep that one caveat in mind. Okay, let's get rolling. Starting at the top, given system feels slow, what's happening? Well, that means understanding process and thread activity. And before we start looking at the tools and the details there, let's make sure everybody is on the same page on what a process and a thread is. And for many of you, this will be review. When you run an exe, most exes I should say, on NT, you're creating a brand new process. A process is an instance of an exe. You could think of a process like a sandbox with acrylic walls around the side and the top. Threads are the kids running around in the sandbox. They can throw sand in each other's eyes, they can kick each other, bite each other, but they can't kick the kids in the other sandboxes because they're protected by that nice solid acrylic wall. So threads running inside a process sandbox or address space have full access to each other's resources. One thread can open a file, another thread can close a file. One thread can allocate some memory, another thread can deallocate some memory. One thread can be using some structure, another thread can be scribbling on that data structure. So it's up to the programmer to manage the synchronization issues if they're taking advantage of multiple threads. Now, if you're a user, how do you know if your app is even using multiple threads? Well, you don't or you shouldn't be able to discern it other than better responsiveness. So one of the advantages of multiple threads is the illusion of better responsiveness. For example, assigning a higher priority to the thread that handles user input versus background processing activities that might be happening. For example, when you do a background print in Word, you do a file print in Word or PowerPoint, the print processing is occurring on its own thread. It can be scheduled separately. And threads are the unit of scheduling on NT. On NT, threads run, processes don't run. Processes contain at least one thread. Whether the initial thread creates additional threads depends on whether the programmer who built that app is taking advantage of multiple threads. Something like Notepad is a dumb single-threaded app. But something like Word, PowerPoint, those are multi-threaded. Of course, most server apps on NT are multi-threaded as well. And one of the advantages of building an app that divides itself into multiple threads is what happens when you run that app on an MP system. Because NT transparently runs all runnable threads on all available CPUs, dictated by priority, of course, a multi-threaded app run on a 2- or 4-way system will, in theory, be able to scale or take advantage of the additional processors. Now, of course, that depends a lot on the kind of synchronization the app does. So a lot of people make general statements about the fact that NT has scaling issues. You can't say anything generic like that because it depends on the piece of the system you're talking about. Is it SQL Server? Is it the file server? Is it SMS? So the way the synchronization is done, how often threads collide reaching for the same structure and have to wait on each other, that's what really dictates how scalable a piece of the system is. And NT5, Windows 2000, has had scalability improvements all over the place. Nothing that you could point your finger to and say, this is the one thing why Windows 2000 now scales up to a greater number of processors than NT4. Every release, scalability improvements in the OS and in some of the key server apps have been taking place in a kind of a gradual or phased fashion. Just to touch on one new process-related kernel object, Windows 2000 has a way to group a set of processes together into something called a job. Now, some of you saw Brian's talk, saw a demo of a piece of user interface in Data Center Server that may appear in Advanced Server or Server, not yet decided, that exposes the programming services. So out of the box, Windows 2000 Professional and Server and Advanced Server don't have any GUI that lets you create jobs, as it were, at least not yet. So what is a job? A job is one or more processes that share a set of limits. For example, physical memory usage, total amount of CPU time, total number of active processes, and also some interesting attributes that will allow some finer grained control of scheduling that you can't get with a single process. There may be some cases where you're going to want to run a process in a job even though there's no other processes in that job. In other words, a single process job, because there's a little throttle or a little attribute on a job that you can't set on a per process basis called scheduling class. Scheduling class is a number from 0 to 9, 5 is in the middle, is the default, and that controls the length of the time slice of the threads in that process or in that job. So a longer time slice, which is the length of time NT lets a thread run before it looks to see whether another thread at the same priority should run. By increasing the length of the time slice, you are percentage-wise giving a little more of the CPU to a set of processes that are still running at the same priority. And that will allow implementation of more traditional class schedulers, where you're saying, okay, this process or this job gets 20% of the CPU, and this is going to get 40, and this is going to get 80, 60. That doesn't add up to 100, does it? You can't get that kind of control with priorities, because if you set the priority of a process higher, how much CPU time does the priority of the process lower get? Zippo. Except there's a little boosting that occurs once every 4 seconds for threads that are CPU starved. We're not describing that here, but so they'll get tiny, tiny bits of CPU time, but virtually zero. But with the scheduling class, you'll be able to, once some products are out that make use of it, allocate, as it were, greater or smaller percentages of the CPU to individual processes or jobs. I'm going to repeat an announcement I made earlier. The crew folks asked nobody to stand against the wall or sit on the back wall because of cables. There's seats around, or you can come up here or sit on the sides. Thank you. Looking at process information, what's running, is kind of a mess. There are almost a dozen process viewer utilities. They all show overlapping subsets of the same thing. The problem is each one of these guys shows one tidbit that the others do not show. Every one of these tools shows one tidbit about process and thread information that is not shown by the other ones. So we will use a number of these, not all of them, but a number of these in this upcoming section. Of course, the most basic one is Task Manager. And without reading the slide, let's just see if you can come up with the right answer for what's really indicated by the tabs in Task Manager, because the names don't really reflect the data they're showing in many cases. For example, the Applications tab is a list of, it's not a list of processes. Programs with visible top-level windows, closer. It's a list of windows. It is a list of windows, that's it. Windows are owned by threads. Threads are owned by processes. So I can't tell, looking at this list, whether I have one process with 10 or 12 windows, or 10 processes, each with a thread that owns those separate windows. So this is not a list of applications. Applications doesn't mean anything. It's not a technical term anywhere in the NT kernel. This is a list of top-level visible windows. By the way, there's lots of other windows in the system right now. Windows that are not top-level and visible. Child windows, for example. Windows on other Windows stations. What's a Windows station? That's the GUI object that encapsulates desktops, which encapsulate Windows. So there's actually a hierarchy that's not really visible in the native GUI for NT, and that is Windows are owned by desktop objects. Desktops are owned by Windows stations. Terminal server, multiple users on an NT terminal server, each get their own Windows station. That's what protects me from seeing the GUI windows on your desktop. Each user gets their own Windows station. And you ever wonder why when you type Control-Alt-Delete, the windows disappear? WinLogon, when you type Control-Alt-Delete, calls a function that's documented that switches to the logged off desktop. So by default, every NT system has two desktop objects on the interactive Windows station, the logged on desktop and the logged off desktop. And you know how many windows there are on the logged off desktop? 0. So there's no windows in the background there. WinLogon popped up the security dialog box, but the windows disappeared because I'm on a different desktop object. Now I'm back to the logged on desktop object. There's a tool in the resource kit called Multi-Desk. Anybody use that, where you can create additional desktops? That just creates another desktop object. Getting back to Task Manager, the Applications tab is a list of the top-level visible windows on all the desktop objects in your Windows station. In other words, if I had used that ResKit tool and created a desktop 2 and 3 and 4, fired up a bunch of apps on those different desktops, they would all show up here in Task Manager. So this is not the list of windows on your desktop, it's the list of windows on all your desktops, of which you normally have 2, and there's normally nothing on the other one. End task means close window. Task is not a term anywhere. These are not tasks, these are windows. Processes are not called tasks. So end task is send the friendly, would you please close yourself message to the thread that owns that window. And you've all seen the message when you bring up, for example, you have Notepad up, you have some unsaved text. I'm going to select the Notepad window, click End Task, and I get the little message from Notepad saying I haven't saved changes. That's because the thread that owned the window, Notepad, received the make yourself go away message and decided not to do that. Meanwhile, Task Manager got tired of waiting and said, hey, the window you told me to make go away, it says end program, but it really should say close window. The window, it says the system cannot end this program. It should be the system cannot close this window because it's waiting for a response from you. End now, however, is a dangerous one because end now shoots the process in the head that owns the thread that owns the window. Which means any other threads that might have been in the middle of doing something are vaporized without any chance to clean up. So that's the shoot the process in the head. End now is the same as, I'm not going to select it, is the same as selecting end process on the process tab. Got that? End now is the same as end process on the process tab. And mapping window to process is quite easy because if you do a right mouse click, go to process. Task Manager flips you to the process that owns the thread that owns that window. So now you can make the mapping of process to window. Now it's hard to see, it's highlighted in gray. I'll select it, now it's in blue. Click End Process. Yes, I know what I'm doing. Poof, it's gone. Okay, so now Process tab. This one actually is labeled correctly. This is a list of processes. But note that the first column is not process name, it is image name. Processes don't have names. There's lots of objects in NT that do have names. Shared memory sections, mutexes, events, semaphores, waitable timers, I/O completion ports. These are objects in the Win32 programming interface that can have global names. When you create a process, you can't give it a name. You can't say create a processor on Notepad and call it Fred. Processes are identified by the name of the exe of which they are an instance of. So if I run 3 copies of Notepad, I've got 3 processes called notepad.exe because they're running notepad.exe. Notice there's 2 and only 2 in the list that don't end in exe. And at the end of this, towards the end of the session, we're going to identify the system processes on the system. And those, in fact, are 2 sort of fake processes because they're not really running a real user mode exe. Every other process in the system is running a real exe. Process IDs, by the way, can be recycled, so they're globally unique while the process is alive. But when the process exits and you run another process, the same number can be used. The CPU column, I think most of you know, is percentage of CPU utilized. And that's the quickest way for me when I'm looking at a slow or seemingly hung system. Bring up Task Manager, go to the Process tab, click on the CPU button, column, and I can see who's chewing up the CPU on this system. Now, of course, I can't do that remotely with Task Manager. That you could do with perfmon. But that's just a real quick way to see what is the offending process that is running right now, which on my system is the idle process. That's actually an illusion because the idle process doesn't run. It's just a fake process that NT uses to account for idle CPU cycles. In fact, on a single processor x86, when there's no thread that wants to run or needs to run, the idle loop actually executes a halt instruction. The system is not running. It's actually halted. So how does it get going again? The CPU clock interval timer is firing in the background every 10 milliseconds. When that fires and it says, oh, we weren't doing anything, it charges that clock tick to this fake idle process. So although Task Manager shows this as the idle process running, in fact, the system isn't really doing anything. Okay, and the last comment on the Performance tab, I'm going to be covering the details of the memory-related counters in my talk tomorrow afternoon, memory management internals. Just to whet your appetite, mem usage, has nothing to do with physical memory usage. Available memory is available but probably very useful and mostly cache data. A lot of people complain that NT won't use more memory, that it's got this available memory and it won't use more of it. Well, in fact, a lot of that is likely cached XEs and DLLs. So we'll talk about that tomorrow in the memory management internals talk. And this performance tab is just a tiny subset of the performance counters accessible with perfmon. This is just 12 counters that the guy who wrote Task Manager thought would be cool to show here. But there's quite a bit more in Performance Monitor. Process Viewer, yet another tool to look at the process list. We're going to use this later when we go to trying to associate activity in the system process, which was that funny process at the beginning that didn't have an XE, with what driver is really the reason for the activity. pviewer, as it's called in the resource kit, same utility, by the way, has a different name in the platform SDK or if you have Visual Studio installed. Lets you, on a per thread basis, look at some details that you don't see with Task Manager or some of the other tools that we've mentioned. In particular, the thread start address. If you think about it, a thread is uniquely identified by the address in memory where the code begins. The start address of a thread is the address in the process address space where that subroutine exists. So in trying to discern if a thread is running, what is it? You need to find out its start address. And then from the start address, somehow get a memory map of the process to find out, oh, where does that fall? Is it in the XE? Is it in the DLL? And again, I'm going to show that tomorrow. Another tool that's quite helpful that we're going to use in the system process tree section is TList with the /T qualifier. And I find many administrators have never seen the output of this. This has been in the resource kit since NT4. And they're surprised to see that NT keeps track of who created who. Anybody here surprised to see that? Raise your hand. That there is a process tree? Everyone knew about it. Windows 2000 in Task Manager, there is a little end process tree option. That's not in NT4, that's new in Windows 2000. Just one note about that end process tree. It doesn't really end necessarily all of the descendants of that process because of the following. When NT creates a process, it makes a record in the newly created process of who its parent was. However, if your parent exits, there's no information to track where you came from. In other words, who your grandparent was. So if you run something that runs something, and the something in the middle goes away, and you pick the top level process and do an end process tree, its grandchild continues to run because the linkage from parent to child to grandchild is gone. All NT keeps is who your parent process was, and that's it. And if the parent process ID is gone, the information is not available. So TList/T uses that information to build this display, and the indentation is just where it can make the connection. If a process is left justified, it means TList couldn't find its parent. Its parent is dead. So Explorer.exe looks like an orphan because its parent is gone. And when we look at the process startup sequence when you log on, we'll see that in fact the logon process runs something that then runs the shell. The something in the middle goes away, and that's why Explorer is shown as an orphan on the left. So we'll come back to this process tree analysis when we look at the system process tree. Another pretty fundamental piece of information you might want to find out on what's going on underneath the hood is what things are opened by a process. Something as simple as you get a file locked error trying to delete or rename or copy a file. Who the heck has it open? There's no tool in the base NT system to look at what files are opened by what process. So that's a pretty basic thing you might want to do. There's two options here. One, there's a tool in the resource kit that's been there since NT4 called OH. The first time you run OH, you'll see a little message that says, a flag has been turned on, and the next time you reboot, you can use me. And the flag that it turns on causes NT to keep a little bit more information about open files than it normally would, 8 bytes per open handle. So you might be wondering, well, how many handles are typical? The Performance tab shows that perf counter. Here's a Windows 2000 professional station, not running too much. I got about 4,200 handles open. I'm not doing very much. So times 8, is that much? No, it's not a significant amount. So a little bit of extra memory per open handle is used to track the information needed for this OH tool to display what files are opened by a process. And that does require a reboot. So once you've rebooted, OH has a couple of selections. One is process ID, object type. The -T is the object type. And many open handles refer to things that don't have names. By default, OH doesn't display handles to unnamed objects. What's an unnamed object? We just mentioned an object that doesn't have a name. Processes. Threads don't have names. So if you just look at the open handle table for a process without saying -A, you're not going to see the handles to other processes and threads. A common handle leak bug is not closing the process and thread handle to a process that you create programmatically. So you have a program that creates a child process. The process doesn't work in exits. You, the parent, the guy who created the child, if you don't close the process and thread handle, the kernel data structures in memory that represented that process and thread hang around until you, the parent, close the handle. So if you wrote a program that created a child process that did nothing but exit, create a child process that exits, create a child process that exits, what's going to happen? NT's memory pools are going to fill up with process and thread blocks for these processes that have in fact exited, but it couldn't release the memory for the process and thread block, just a small data structure that describes the object, because you, the parent, still have a handle open. So what might appear to be a system memory leak, one of the memory pools is going up and up and up and up, in fact is a process with a handle leak. And that's one of the little details you can add in the Process tab with Task Manager. If we go to View, select Columns, handle count. And you might be interested in thread count as well. And by the way, here's the new I/O counters that were added in Windows 2000 to look at I/O statistics on a per process basis. But just something as simple as sorting by number of handles and looking perhaps for a process whose handle count is going up, that's not going to appear as a memory leak in the process per se. It's going to appear as a memory leak in the system, again caused by a handle leak. This process is not closing handles. Now when you kill a process, all the handles are closed. So if you have a process that has a handle leak and you exit the process, all the things referenced by that are going to get closed and then deallocated. So that's, to me, an important thing to know about. The problem with OH, as I mentioned, is needing to reboot and running with a special flag. So the alternative is a Rasinovich tool called HandleEX. HandleEX, though, loads a driver. So the first time you run it, it installs and loads a driver. And the reason it needs this driver is it's reaching into data structures inside the process that are not accessible from a user program to dump the handle table. So let's go ahead and run that. HandleEX. One of the things that Mark's handle display utility does a little bit better than the resource kit tool is, if we sort by object type and we look at the file objects, full path names. Let's find something more interesting like my PowerPoint. Here's PowerPoint.exe. I'm going to sort by object type, look for the file objects. File. Oh, there. And there's my PowerPoint. There's the PPT file with the full path. Let's do a contrast and show the same information with OH. OH minus P, what's the process ID? 844. Minus T file. So in other words, only show me objects of type file. Notice what's missing in the path? No drive letter. So OH doesn't show the drive letter. Mark's tool shows the full path, including the drive letter. That's the one thing Mark's does better than the resource kit tool. Okay, so pluses and minuses with both. Another basic piece of information that you might need to analyze is what DLLs got loaded in a process. You're having DLL conflicts. Of course, on Windows 2000, that's solved, right? That'll never happen again. But just in case it does, what could we do? Well, there's kind of two views of what DLLs an application uses. The static view and then what actually got loaded when you ran the thing. And what actually got loaded when you ran the thing depends on what path was, because there's a series of steps that the image loader goes through in terms of looking for DLLs. It looks in the directory where the exe was, then it looks in path, then it looks in some system directories. The static view may be useful to look at just because you're able to see, okay, this exe, when it starts up, sucks in the following DLLs. And the dependency walker tool in the resource kit, it's called depends.exe. It's one of those tools that gives you a feeling of security, depends. When you install the resource kit, adds a little entry to the context menu. So here I am in my WinNT System32 directory, and I'm going to look for notepad.exe. There it is. Right mouse click, view dependencies. You can also run it directly and then open an exe. So right mouse click, view dependencies, and all this is doing is walking the static data inside notepad.exe to dump out what DLLs Notepad is linked against. Which DLLs, in other words, will be opened and loaded into this process address space when this exe is run. Now, by the way, DLLs are loaded dynamically all the time. So this doesn't show you DLLs that get mapped in later because somebody explicitly called a function to load them. This is the ones that get sucked in when the process starts. So that's interesting, but that doesn't tell me where they're going to come from, does it? It's just their names. So it would be neat if I could see, given that a process is running, what was the full path name of all the DLLs that got loaded when the thing ran? Or for that matter, what's the full path name of the exe running? So let's go back to our scenario. If you bring up Task Manager, go to the Process tab, you click on the CPU column, and you're trying to figure out what processes are running on the system that's making it run so slow. And you see, oh, it's hh.exe. But you say, I don't know what hh.exe is. If you knew where it was, that probably would answer your question, right? If you knew the path name of where the exe was on the disk, that probably would answer your question. So how can you find out the name of the path where the exe was pulled out of? Anybody? You could do a dir hh.exe/s, but what if it was off some network drive letter that you would run? You could go do a dir on all your map drive letters, but what if it was a UNC path that you ran it off of? So basically, dir won't do it. Find files won't do it either, because you're not able to. You're going to have to search every server in the whole network. So that's basically a slow and actually not. You can't find them all. Trying to do it through find file. So a couple of options here. Shall we wait for the telephone call? Get that man a vibrating battery. Okay, so back to our question, what's HH? I do one of two things next. One is I do a tlist/t, because tlist/t tells me who its parent was. Sometimes knowing the parent of a process answers your question. Now in this case, hh.exe was created by Explorer. Well, that means it's something that I ran. I still don't know what it is. Now pay no attention to the window title there. Resource Kit Online Books. We already found the answer to the question, because tlist does show the title of a window in that process, not the window, because processes can have more than one. That's the title text from the window, from a window owned by a thread in that process. But let's pretend it had no window title. tlist space hh. So if we look at the qualifiers for tlist, there is a pattern. Pattern can be a process name, not task name. There's no such thing as a task. So tlist hh. Now this looks interesting because the command line is included. And the command line was whatever was passed to start that process up. In this case, the command line had the full path. It's a file in the WinNT directory, so it's a piece of NT. And there's the argument that was passed to it. We also see in the bottom a list of the DLLs, but what's missing in the DLL list? Path name. In fact, the path name for hh.exe is only visible to us because whoever created that happened to specify it in the command line. For example, if I said tlist, just to illustrate this, can you tell where tlist.exe is from the command line? No, because the command line was tlist. And again, the list of loaded modules, the exe and the DLLs, doesn't have the full path name. So our answer, our friend, Mark Rusinovich, list DLLs. List DLLs is a safe tool in that it doesn't use a driver. And let's go see what happens when we do a list DLLs -p hh. Now we've got full path names for the exe and all the DLLs that got loaded. So if you want to see the huge array of DLLs loaded by pieces of Office 2000, fire a process up, do a list DLLs. Okay, so for me, list DLLs is an important diagnostic tool. That is the only way I know of anyway on an NT system to see exactly what DLLs were loaded into the process and their full path name. Okay, so that was kind of the basics on just looking at process activity, trying to map a running process to the path it came from. Let's look a little closer and try to get some idea of when something's running. What's going on? Is it spending time in the OS? Is it spending time in the application? The system, again, feels slow. What's running on the system? And in order to do that, we need to understand some basics about how NT accounts for CPU time. When a thread is running and the clock interval timer fires, and it's about to charge this clock tick to somebody, one of the key pieces of information that tells it where to charge this clock tick is what mode the processor was in. And the processor is in one of two modes, privilege mode or user mode, or sometimes called kernel mode or user mode. Now that's the generic term. On the x86, it's ring 3 for user mode and ring 0 for kernel or privilege mode. The Alpha AXP platform actually has those by that name, kernel mode and user mode. So although NT runs on platforms with more than one memory protection or access mode, it only uses two. Every page in memory that a process can see has a single bit that says whether or not it is a kernel or system page. If the bit is on, it means that in order to touch that page, read it or write it, you must be running in kernel or privilege mode. And we'll talk about in just a minute how you get into kernel mode. So if you're not in kernel mode and you try to touch a piece of operating system data, you get an access violation. And that's why user processes on NT cannot, by accident, go corrupt some system data structure. There are no holes, unlike in if I can borrow the phrase from Mark Manassi, Wintendo, Windows 98. I love that one, Mark. Wintendo. It's good for games. Windows 2000 is better for games, but Windows 98 does okay. In Wintendo, there's some major holes in the address space, pieces of operating system data structures that don't have this magic flag on, which means that a user application, written in C or VB for that matter, that happened to have the right address could go scribble on some piece of operating system data and cause a system crash. And those holes can't be closed in Wintendo because they would break some existing DOS app. NT didn't have that as a constraint, and so there are no holes. There's absolutely no way that a pointer that's gone amok, that's been corrupted in a user application can accidentally scribble on some piece of system space and cause a corruption in some operating system memory. Now that sounds wonderful, but that's ancient technology, right? Unix has had that for years, VMS has had that for years. And by the way, just to be fair, NT's memory protection model for pieces of the OS is not very granular, because all drivers and the NT operating system run in kernel mode. They all share the same sandbox. So we talk about processes as sandboxes with the kids running around. All the drivers and the OS are in the same sandbox and can throw sand in each other's eyes. Now I have a mention later of the driver verifier tool in Windows 2000, which helps to isolate memory corruption problems, but still a bug in a driver in Windows 2000 NT4 that causes a pointer to be corrupt, that driver can go scribble on any piece of system memory it wants to because it's in kernel mode, and memory protection is that simple A-B. It's either a kernel page or it's a user page. And all drivers, as well as the OS, run in kernel mode. They're all in the same sandbox. There's no memory protection between drivers or OS components like there is between processes which run in their own sandbox. Because processes don't run, threads run, the access mode is really an attribute of the thread. So when a thread is running, it's running in either user or kernel mode. And when the thread is running and the clock interval timer fires, if the access mode of the thread was kernel, that tick is charged to that thread's privilege time. Now let's take a look at the counters as they appear in perfmon. And the reason we're looking at this is that if you bring up Task Manager, click on the CPU column, you're seeing a pretty dumbed down view of what's really going on in each process. You're seeing the total CPU time, but it doesn't show you the split between user and kernel mode. It doesn't show you how much time the threads in that process are spending in the OS or drivers versus in the application. And you get a global view of that on the Performance tab if you do the View Show Kernel Times. Now we see the split between user and kernel. Red is kernel, green is user. But still, it doesn't help me because I don't know right now which process is taking up that 100% kernel time. So perfmon lets us bring it down to the thread or process granularity. I'm going to clean off my graph here. And click on the plus sign. And let's just look at the 4 levels of granularity that NT keeps CPU time. At the topmost level, the system as a whole, there is a percent. You know what? It's in moved processor. We can get it with total there. Processor object. Privilege time plus user time equals processor time. So the time spent in privilege mode on a processor granularity is overall, it was that red part in the CPU display in the Performance tab, but it shows me on a global basis for either a given CPU or all of the CPUs, depending on which counter I select, how much time the CPU is spending in kernel versus user mode. Now that might be interesting because it does tell you, is the thing stuck in an application? So if it's all user mode, then some application's in a loop, stuck in itself. Is it mostly kernel? Well, it could be a piece of NT that's running away. It could be some driver running away. It could be an application that's making lots of system calls because system calls execute in kernel mode. So more interesting would be to drop down to the process granularity. Same counters, privileged, user, and processor time. Now we see a list of processes as opposed to processors. The problem is, and we're going to see this in a couple of slides, there's a key piece of processor activity that is not charged to any process. In other words, there's a key piece of activity that if it's going on, doesn't show up here. Interrupt time and post-interrupt processing. Time spent processing interrupts and the follow-up time to do that is not charged to any process. So simply looking at the process activity on the system, you're missing something. You're missing interrupt time. So let's take a look at the theory behind it and then the performance counters that you can look at this directly. So number 1, we mentioned already. NT spends time in kernel mode because programs ask it to do something. Open a file, create a thread, allocate some memory. So as an application makes system calls, the execution of that system call, creating windows, drawing on the screen, is going to be charged as kernel mode time. So if you're looking at a particular process that's gone runaway, something's running and running and running, you might be interested to, in perfmon, drill down, pick that process, and look at the split between privilege and user time. In fact, let's take a look at the dependency walker. This is a pretty boring one. Now, right now, dependency walker is quiet. So I'm going to go and make it run by dragging the window around. The green in this case, if you can see the bottom of the screen, is privilege time. The blue is user time. Why is it more green than blue? Because it's redrawing itself all over the place, and windowing activity occurs in kernel mode. The bulk of the windowing system since NT4 was moved into kernel mode as a huge loaded driver. The blue represented the time in the application calling the windowing functions. So that's a quick way to look at a particular process and say, is this guy stuck in itself? If it was 100% user mode, it would be stuck in itself. Or is it making lots of system calls? You'd see some blue and more green. So that's case number 1. A process is asking the system to do something. Case number 2 is what we're covering next, which is interrupts. Interrupts occur hopefully because somebody asked the system to do something. An I/O was initiated, for example, or somebody on an NT server is coming over the net to do I/O to the file server driver. How's that processed? Well, whatever was running on the system is, boom, ouch, interrupted. There's this poor little thread running on the side. It's interrupted. The time spent servicing this interrupt is not charged to that thread. It's charged to a performance counter called %interrupt time or interrupt time. There is no context switch. NT doesn't have to do much work to start processing this interrupt. That's one of the things that's sort of well respected about NT's interrupt handling mechanism. There's no separate interrupt handling thread. NT doesn't switch to some other thread. The thread that was running is interrupted. Its machine state is saved. NT calls the driver responsible for that interrupt. He does his work, returns to the system, which dismisses the interrupt, and the thread that was running continues execution. Now, of course, the system could have been idle also. This is an example of something was running when the interrupt occurred. Now, there's two performance counters, though, that summarize interrupt time. One is called interrupt time. That's simple. The other is called DPC time. What's DPC time? Well, if you click the explain button, the simple explanation is not here. This is not really a simple explanation, which is why we're going to do this next slide. In order to understand DPC time, we've got to look at how NT prioritizes servicing of interrupts. On an x86, NT defines 32 levels of priorities for interrupts. This is completely a software concept because when an interrupt occurs on an x86, the processor is actually interrupted. So it's the OS that's saying, oh, this is a level 9 interrupt. We're in the middle of processing a level 10 interrupt. Thank you very much. We'll take care of that later. And it dismisses the interrupt. So this is done in software on the x86. It's actually done in hardware, or actually PAL code, microcode on the Alpha, which has 8, not 32. What we're really interested in here, though, is what's the difference between the ones in red versus the ones in blue. When an interrupt occurs, first of all, what's not happening anymore on that system? Process activity is interrupted because threads run at interrupt level 0, sometimes 1. 0 and sometimes 1. That means any interrupt will interrupt the highest priority thread in the system. And just to confuse things further, thread priorities have the same numbering scheme. Thread priorities go from 0 to 31. This is a completely different number because this is the priority of the interrupt on a per processor basis. This is a global priority on a per processor basis. One processor could be at interrupt level 5 and another one could be at 8 and another one could be at 0 on an MP system. So that's one thing that's stalled, thread activity. Second thing, delivering interrupts is stalled at that priority level and below. So in order for the driver to minimize the time it's blocking other interrupts, the OS provides a mechanism for the driver to say, thank you very much, I've captured the information I need. Please call me again later at a lower, less severe interrupt level. And that mechanism is called deferred procedure call, hence the name DPC. And deferred procedure calls are just a way for a driver to get called later, to defer their work. Now, what number is this associated with? Let's go back to the chart. It's number 2. Number 2, or priority level 2, is where deferred procedure calls are processed. 2 is above 0 and 1, which means that those guys will all get finished before any threads can continue running. But it's below any of the red priority levels, which is where device interrupts occur. So the driver, as it's finishing its work, is not blocking further device interrupts. When the clock interval timer fires and the current priority level of the processor is 2, that's when NT charges that clock tick to DPC time. So you could think of interrupt time as being sort of phase 1 of an interrupt, and DPC time, phase 2. I'm simplifying it a little bit because there's a number of cases where normal threads that are calling system calls, inside the system call, the IRQL, that priority number, is raised, which means that if you're running an app and the clock happens to fire while your thread was in a system routine who had raised IRQL, NT may charge that to DPC time or interrupt time, and it wasn't either of those. Does that make sense? Normal thread activity, calling a system call, for example, anything having to do with scheduling, changing priority, creating a thread, creating a process, during the time that the thread's doing that work, it's running at IRQL2. The clock is firing and says, oh, we're at IRQL2? We must have just spent the last 10 milliseconds doing a DPC. In fact, we weren't. We were in some user thread. So it's not 100% accurate. So it's not true to say that interrupt time is 100% interrupts and DPC time is always deferred procedure calls or interrupt phase 2 because of what I just described. But most of the time, or for the majority of the CPU time, that's true. So tying this back to looking at CPU activity, looking at the list of processes on the system, and what's running doesn't show you interrupt time and DPC time. So to get a 100% map of the CPU time on the system, if we go to the next slide after this, you must look at interrupt and DPC time. So the total CPU time on the system is the time spent running processes plus interrupt time plus DPC time. And if you leave those two out, you're missing or potentially missing something that's going on. System feels slow, nothing appears to be running, it's got to be interrupt or DPC time. Now your next question might be, okay, how do I find out what driver is responsible for the interrupts that are occurring? Answer, there is no tool to do that other than setting breakpoints in the interrupt handling code in the kernel. So there's no easy way to find out, given interrupt time or DPC time is up 2%, 5%, 10%, who's actually responsible for that. Okay, two more topics. We have till 2:45? Is that right? Okay. What we're going to do next is just take a tour down the system process tree. And we're still with the same kind of scenario here. Something's running. What's going on? And now this time, the something that's running is not something you ran. It's a piece of the system. Now, some of the system processes have names that are somewhat descriptive. Some do not. So to me, it's helpful to be able to accurately identify every process running on the system. So when it's running, you know what and hopefully why it's running. The tool we're going to use to kind of walk down this display is TList/T. And let me just make a little plug here, by the way, for a new tool in the resource kit, in the Windows 2000 resource kit, that is not installed when you install the resource kit. This is a strange one. There's a help page on how to install it. It's in the resource kit directory on the hard drive, and it's called ptree-g, and ptree is the command line version. This is just a GUI version of the same information we were looking at with the TList command line tool. I'm not using this for the demo only because this doesn't actually get set up when you install the resource kit, full resource kit, and it's not in the free resource kit subset. TList is in the free subset that everyone gets. The one nice thing about ptree, though, and the reason I wanted to mention it, it's a client-server app, so it has an NT service component you can install on a remote workstation or server, and therefore you can use it to look at the process tree on another machine. That you can't do with TList. You can do that with pviewer. Pviewer takes a computer name, so you can look at the process list on another machine, but you can't look at the process tree, and to me the tree is more helpful. So ptree in the Windows 2000 resource kit does allow you to do that because it has a service component you can install remotely. Okay, back to TList. Let's start at the top and go down. First note, and this is mentioned on the bottom of the slide if you look in the PowerPoint towards the bottom, the first two processes in the list have different names in different utilities that display the process list. For example, TList calls this process ID 0 system process. Task Manager calls it what? System idle process. The process ID is the same in both cases. It's PID 0. The reason that you'll see these show up with different names in different utilities is because they have no name. It's blank. Each utility makes up the name. And they make up different names. Because again, these two processes aren't running in XC. They're the only two processes that aren't running in normal user mode XC. Okay, PID 0 is the idle process, despite the name that's shown here. And we mentioned briefly what the idle process is. It's just a fake process to account for idle CPU cycles. It's not actually running anything per se. On an MP system, there's one thread per CPU, because one processor could be busy and the other processor could be idle. So each processor has its own clock interval timer, and when that clock interval timer fires and there's no currently running thread, that clock tick is charged to the idle thread, which again isn't really a real thread. There is actually an idle loop on an MP system. When a processor goes from running a thread to idle, it does fall into a loop. And the reason that it's actually running and not halted is because it can go drain the DPC queue from other CPUs. So interrupts might be occurring on CPU X. The driver is doing its work. It queues a DPC Wouldn't it be nice if another CPU could go process that deferred procedure call while the first CPU is finishing that interrupt, or maybe process servicing other interrupts? So any CPU can grab the phase 2, or the sort of second step of interrupt processing, from any other CPU's DPC queue. And that's what's happening in that idle loop. They're spinning, looking for DPCs and other CPUs' DPC queues to go do the work. The next process, which I call the system process, TList calls it system, Task Manager calls it system, some call it system process. This process is an interesting one because it's the home for such a wide variety of stuff that the fact that it's running is meaningless. I mean, you can't conclude anything other than, oh, some piece of the OS or some driver that makes use of system threads was running, which is basically tells you nothing, right? So let's take a look at how we can drill down inside this process to find out what's really going on. And in order to do that, we've got to look down to the thread granularity. Now first, let's talk about what some examples of system threads. System threads are normal threads in that they're an instance of a piece of code that's running. They have a priority. In fact, they don't get any special scheduling preference. They have a normal priority like any other thread in the system. A system thread running at priority 10 doesn't supersede a normal user thread at priority 10. And not all drivers create system threads. System threads are used for pieces of the OS or drivers that need to have their own life. They need to be able to run concurrently with other user activity. A real simple example of that, if we just go to the next slide, is the swapper. When NT decides that a process is gone idle, it marks its physical memory to be sent out to the paging file. The private process part of its physical memory to be sent out to the paging file. Who's going to do that work? NT needs a thread. It's not going to take somebody else's thread away. So in the background, or concurrently with other thread activity, this little system thread wakes up and he starts grinding out this process out to the paging file. The cache manager has lots of a number, 2 or 3 system threads. For example, when you write data to an open file, where does the data go? It doesn't go to the disk right away, it goes to memory. NT's default behavior is a deferred write. There is a way to open a file programmatically and say, hey, when I write to this file, I want the data to go to the disk right away. Don't cache it. But the default is to cache data. So who does the work of later writing out cached data to the disk? The cache manager has some system threads that get woken up and they go do that work. So these system threads are running concurrently with user thread activity. And again, what dictates who gets to run is simply the priority. Another example of system threads or use of system threads is the file server. What process appears to be running on a heavily loaded NT server system that's being used as a file server? If I go do a dir /d Solomon $/s, so I'm doing a directory of my laptop over the net. I bring up Task Manager and I click on the CPU column. Do we see the system process running? Yep, see it? 5, 6, 7, 5. You might be wondering, why is that top one, CSRSS, taking up almost half or more of the CPU? We're about to identify that guy in a second. That's the windowing system process. So I'm going to come back to why he's running now. But notice the system process is in fact running. And the reason that the system process is running is that remote client requests for file server I/O. So you're on a client, you go ask for some data off the disk of a file server, are processed by system threads. System threads appear in this generic system process. So although I knew what was going on, if I really wanted to find out why the system process was running, I'd have to do what? Drop down to the thread granularity and find out what threads were running and then somehow map that to the driver. And that's what we're going to look at next. So I hope that's clear on some examples of system threads and how they're used. If you're interested in the programming side, they're fully documented in the device driver kit because customers who write drivers may also have the same need to create system threads. So the DDK, or device driver kit documentation, which is available for free on the MSDN website, or if you want to download the whole DDK, that's freely downloadable from the MSDN homepage. Actually, no, it's the hardware developers home page. I'm going to write that down here so in case anybody wants to download that. Microsoft.com/hwdev. Let's just get a bigger font here. Okay, this is the home page for driver writers. So if you're interested in the DDK, which has lots of interesting tidbits about NT internals, that's where you can download the Windows 2000 device driver kit. So we have the system process running, like in the example we just saw. We want to find out what driver owns the thread in the system process that was running, or the threads that might have been running. So we've got to find out which threads were running, first of all. And that we can do with perfmon by going to the thread object. And here's a question. Which counter do I want to select? Processor time, privilege time, or user time? One thing about system threads that is different than all other threads is that they only run in kernel mode. They have to be running in kernel mode because they're subroutines inside device drivers, and device drivers access system memory. So in this case, privileged and processor time are identical. They equal each other. User time is 0 for any system thread because, again, these threads are running inside OS-protected memory. So we'll pick processor time. It doesn't really matter which one. We'll scroll down to the system process. And the sort order here is not very helpful. It's sorted by alphabetically as opposed to numerically. So thread 0, 1, 10, 11, 12. I'm going to scroll down until I select all the threads in the system process. Click on Add. Click on Close. We're now looking at the system thread activity on a per thread basis. This is, to me, like one of the highlights of the afternoon. Here, by the way, you're supposed to go, ooh, ah, wow. And if we went back and did our dir d Solomon /s, we see some system threads running. Wow. This is how I get my jollies, guys, so can I say. So the next question is, what threads were running? I'm going to click Stop so we don't lose that. And we hit our helpful Control-H, or turn on highlighting, and then scroll down until one of those lines goes white, which in Windows 2000 takes a little longer than it did in Windows NT4. Hey, it may be slower, but at least it takes more memory. Oops, sorry. Thread 29 ran there. Let's just pick on him. I really would need to look at all of these, by the way. We're just going to pick one. Where is thread 29? Remember the one piece of unique information that differentiates all threads? The start address. Somehow I need to find the start address of thread 29. And pviewer tells us that. So I've selected the system process. I drop down to thread 29. And it's FCB22E52, where I'm moving my mouse. Probably not legible from the back. So again, pviewer does show the start address of every thread. Now my next question is, what's at that address? And in order to find out what pieces of the system are loaded at what address, if you go back to the slide, so we just did step 1. We just did step 2. Step 3 is to run pstat. And pstat, I think I had it already up here. No, I'll run it again. Pstat is a process status utility that dumps first the processes in the system, and then every thread inside each process, with a little more details here. We're kind of ignoring the details going by here. We're interested in this display, which spits out at the end. So at the end of pstat, a very important display that comes out that only comes from this utility, and that is the address in system memory of each loaded kernel mode module. Now, I didn't say device driver because the first and second are not really drivers. NTOS is the OS. The HAL library is not really a driver per se. So this is the list of loaded kernel mode modules in system space and their system virtual address, where they start, not where they end. If you want to figure out where they end, you've got to add the code and data column. But we're going to hope that this number is near something obvious, so we don't have to do our homework. Now, I could get caught here and have to go do the homework, which we're not going to have time to do, but FCB22. So we're looking for FC something. FCB, what was it? 22. And you know, there's FCB 10000, and I was doing a dir of my C dollar over the net. So guess what? We found it. It was the file server driver. Now, I kind of knew the answer there, but do you see how we just made the mapping of system process was running, which thread was running, we got the start address, we found out, and I skipped the detailed work of adding the columns to see that that thread falls within the range of that driver's memory address. Okay? Thank you. Sure would be nice if there was a tool to automate that. Now, just to make it a little bit yuckier, what if the thread's start address, let's go back to the beginning here, we had hit one of these guys. Pick this one, 804AF. And we look at our little pstat output. And guess what's loaded to 804 mumble, mumble, mumble? The OS. The first N threads in the system process are actually subroutines in the OS. So now what do you know? If you're running perfmon, you're looking at system thread activity, and you find out that thread 3, 4, and 9 are running, and they're all inside NTOS kernel.exe. What do you know? Nothing. I mean, you know, maybe that's enough for you. It's not enough for me. I want to know what piece of the OS. Is it in the swapper? Is it some piece of the cache manager? What's going on? So now we have to go a little bit further and find out the name of the subroutine at that address, because the fact that it was in that driver wasn't enough. And that's actually not that hard. Because Microsoft ships the symbol table files for all of the XCs, DLLs, and drivers on the Windows 2000 and NT4 CD, if you are able to dump that symbol table file, you'd have your answer. And there's a tool in Visual Studio, Visual C++, called dump bin, some of you might know of. But since most people here probably don't have Visual Studio installed, there is a backwards way of using the kernel debugger to dump the loaded symbols. And we're about to look at, in the next section, the kernel debugger. Given that you have the kernel debugger up, either you're looking at a crash dump file or a live system, there's a single command called x. X that evaluates the value of a symbol. If you say x space Fred, it gives you the value of Fred. If you fire up the kernel debugger, opening a crash dump, the default symbol table file that's loaded is the symbol table file for the OS. So if you type x space star, guess what you get? The value of all the symbols in NTOS kernel. You then look up the start address of the thread that you were interested in, and hopefully, not in all cases, but in most cases, up will pop the name of the function at that address. And here is some sample function names. This was done in an NT4 system by, again, looking up start address of thread in the symbol table file output for NTOS kernel.dbg. This is done without source code because, again, Microsoft ships the debug symbol table files, which contain the names of all the global symbols inside that exe. So you'll see things like KE, swap processor stack. Well, it doesn't take a rocket scientist to figure out, oh, that's the swapper. Or you might see some routines that start with CC. Those are cache manager threads. Now, if you're interested in the abbreviation listing, I have that in my book. Most of them are self-explanatory. EX is executive, MM is memory manager, KE is kernel. So with a little more digging, you're able to now map system thread to name of function in the kernel. Okay, we just identified two, and only two of these processes in the system process tree. Let's finish the rest. Looking at this display, what's the first real created process in the system? SMSS.exe. That's the first real exe that comes to life. And SMSS.exe really doesn't do much after the system is up. So it's responsible for launching the rest of the system. It looks in the registry in a registry key underneath current control set control called Session Manager. You might have looked there before. We're not going to peek in there now, but that's an interesting place to look. And most of those registry keys are documented in the registry entries help file in the resource kit. The first process that the Session Manager creates is the windowing system. If you look in the registry at this location, the registry key called Windows has a value of CSRSS.exe. CSRSS stands for Client Server Runtime Subsystem, but really it's the windowing system. That process is what's left of the windowing system because, again, in NT4, the majority of the windowing system was moved into system space as a kernel mode driver. And if we could just flip to the next slide, this process rarely runs. Now, we saw it running like crazy when I was doing that command line dir. One of the things that causes this process to run is any output or input to character cell or console applications. So in other words, if you're running the command prompt, which is a character cell app, when I move this window, who's repainting it? This is a dumb character cell app. It doesn't understand repainting. The windowing system process does it. Or when I do a dir, the scrolling and all the painting of the text in this window is done by another process, CSRSS. So if CSRSS is running a lot, your probable first cause is some command line process doing output to a command line window. Got that? There's a few other cases listed there, but those are fairly seldom, or they're not going to account for a significant amount of CPU time. Okay, so we talked about SMSS, we talked about CSRSS. Next in the tree, WinLogon. And WinLogon, by its name, everyone knows is the logon process. The first thing WinLogon does is create a child process to run the service controller, who is then responsible for launching all of the services defined in the registry to start automatically. Now, some services get started even though they're not defined to start automatically if another service depends on them. One of the attributes of a service is the services that you depend on. So a service that you have marked as manual may still get started because a service that depends on that service starts. So this is just a real quick way to find out, given a process is running, is it a service process or not? By doing a tlist/t. If it's parent to services.exe, you've answered your question. Yep, it's a service process. Services.exe, by the way, does more than just service startup and shutdown. So let's talk about this for a second. When the system boots, the service controller looks in the registry, builds the dependency graph, starts these child processes, the service processes, but several NT services live inside this process as well. For example, the event log, the workstation and server service. How do I know that? Because if you went through the work of mapping the event log service to find out which process it's inside, you would see that the name of the exe that contains that service is services.exe. So I mention that because some think incorrectly that if they look at the process activity on the system and the process that's running is services.exe, that somebody must be starting or stopping services. Not true. Several base NT services live inside that process, in addition to the actual infrastructure code for starting and stopping services. So to make that mapping, just do a search in the registry underneath HQ local machine system current control set services for the name of the exe. What's going to pop up? The name of the service. Now the name of the service, there's actually two names for every service, the internal name and the external name, and some of you have seen this before. If you use the resource kit, is it SC list? Yeah. Here we see the two names. This is the internal name, for example, Landman Workstation. That's the name of the registry key. Workstation is the name that the administrator sees. That's called the display name. But what isn't shown here? The exe. So here's a list of services. I can't tell which process those services would be in, or what process would be running when that service is active or doing something. That's what takes us to have to go to the registry and look up the name of the service. So you can either go from name of service and find out the exe it's in, or name of exe and find out the service or services inside that exe. And that allows you to pinpoint down process activity for processes that you know are services just by virtue of the fact that they are children of the service controller. We're going to run probably just another 10 minutes over, so if you got to go, but we're going to go just a little over time. Okay, that's it on mapping processes to what's really running. I left one out that was on an earlier slide I just wanted to touch on, and that's LSASS. There. Come on. LSASS is the security server process. That's the guy that has the SAM open. When you log in locally, WinLogon sends your username and password to LSASS. He looks in the SAM. If you typed in the right password, logon continues. But the activity of doing the authentication, as it were, is inside this process. So on a heavily loaded NT4 domain controller at 9 in the morning when everybody's logging in, what process is active? LSASS. That's the guy that has the domain SAM open. And when we were looking at the basic output of TList and noted that Explorer was an orphan, this is why. When you log in, NT runs something else, which then runs Explorer. And that something else is called userinit. That's also in the registry and configurable. There's a registry key called userinit, whose value is userinit.exe, as well as other things that might be configured to start before the shell. So there is a way to configure NT to run something even before the shell starts. You can also reconfigure what shell gets run. For those of you that don't like the GUI that's provided, you're certainly welcome to change it to something more obscure, like, let's go back up here to Windows. So this is in the software configuration, WinLogon, shell. For example, all you VMS fans might prefer DCL. Unix people prefer the shell. We certainly don't need to run Explorer to be able to use NT. Task Manager still comes up, so that's a way to change the shell. Now, what was the original name again? There we go. Okay, last section, understanding process and system crashes. How many people have ever seen Dr. Watson come up? Dr. Watson looks different in NT5. I'm going to run something that dies. This is a little C program that performs an invalid memory reference. So it doesn't say Dr. Watson anymore. It says program error. Acvio.exe has generated errors and will be closed by Windows. You will need to restart the program. An error log is being created. This dialog box is as useless as the NT4 dialog box. The dumb user doesn't know what to do. It doesn't tell you where the log file is. At least it could tell you that. Where is the log file? Well, if you run Dr. Watson interactively, so I'm going to do a drwtsn32, it detects that it's being run interactively as opposed to by a process that's dying, and it does show you the configuration information, for example, the log file path. So Dr. Watson log files go to system root, which is WinNT. So there's my Dr. Watson32.log, and very few administrators I talk to ever go and take the proactive step of looking for Dr. Watson logs on their users' workstations. The very presence of a Dr. Watson32.log means an application died. Applications aren't supposed to crash. Every Dr. Watson32 log entry, in theory, should be a bug report to somebody, some internal group if it's an internal app, Microsoft if it's a bug in a Microsoft app, although I've never seen that, or some third-party vendor. Let's take a look at this. Although there's a lot of gibberish in here, very simply at the beginning, we have the name of the exe, which might be enough, the list of processes running on the system, not terribly interesting, and then for the programmer, a pointer to the address in memory of the instruction that actually faulted. So is that going to be useful to a support person? No. To the developer of the app? Maybe. What's probably more useful is this, the crash dump file that was created. So one of the configuration options here was where to put the crash dump, and the default on Windows 2000 and NT4 is to create a crash dump file. This is not an NT core dump. This is completely different than what most people think of as a crash dump. User.dmp contains the private process memory in the process that died. In other words, the part of the sandbox that is not the exe in the DLL. So user.dmp doesn't have the exe and the DLLs that were loaded, just the private process memory. That is the dead body awaiting analysis by a coroner. And a vendor who tells you that we don't know how to process user.dmp files has problems, because they should know how to do that. That file can be opened by a debugger, and the programmer is looking at the state of that process at the time it died. So it's fairly straightforward for a developer to use this to look at the process at the point that it died. So some vendors will say, well, tell me exactly what you did so we can reproduce it. Rubbish. They should be able to take one of these things and look at and debug and look at the state of variables and so on. So that's what user.dmp is. The problem is this is overwritten every time. Dr. Watson 32.log is appended to, this is overwritten. So if you don't have some mechanism or smart enough users to go rename or copy that, you're only going to have the most recent one. So I hope that explains what Dr. Watson and user.dmp is. If you're really slick and you've got multimedia machines, you can also play a WAV file. For example, we in support apologize for the unexpected termination of your application. Please dial the help desk at so and so and so and so. Okay, last topic. System crashes. Personally, I've never known NT to crash, but if it did, what could you do? Number one, now this is changing certainly year by year. Very few people outside of Microsoft really do serious crash dump analysis other than device driver writers. How many people here do serious NT crash dump analysis that don't work for Microsoft? 1, 2, 3, 4, 5, and 6 out of, I don't know, we got 900 people in the room. I'd like to meet you guys afterwards, by the way. Interesting article on Mark Rusinovich's website on why the basic output from a blue screen, or even the basic information you might look at in a crash dump, often will not tell you easily, without some serious digging, who the culprit is, because it's often the victim that trips on the wire causing the system crash. So some driver has a bug and corrupts some piece of system memory. Later on, some piece of NT trips on that, uses that structure. So it appears that NT had a bug. An access violation occurred inside the kernel, but what was it? It was some driver that corrupted some memory that it later tripped on. But you know, just simply pulling out the crash code in many cases at least points you in the right direction. And very few administrators I've talked with know how to go through the basic steps of opening a crash dump file and just pulling out the crash code. Forget using the analysis commands and looking at data structures and so on. Just pulling out the crash code. Now, of course, if you've got users that are very careful and write down all the information on the blue screen, maybe you don't need to do this. But I don't know about yours. Very few users I know of wait to do that. And of course, the default on NT Workstation is to do a reboot anyway, so it disappears. Now, just as an aside, Rusinovich has got a cool blue screen save utility that saves the output of the blue screen in a text file. That's useful because on some systems it's not practical to have to be able to take a crash dump. In order to take a dump on NT, you must have a page file that, come on, this is a serious topic here. You must have a page file in NT4 on the C partition at least the size of physical memory. Now in NT5, Windows 2000, there is an option on the crash settings, so in Control Panel System, Advanced, Startup and Recovery. Boy, if you knew where anything was in NT4, you know it's not there in NT5. So under Startup and Recovery, and by the way, the default in Windows 2000 is not to do this. In Windows NT4 it was. Normally, the type of crash dump that's created contains all of RAM. There's a new option in Windows 2000 that says write kernel information only. That means don't write out to the dump file the process memory, only OS data structures. So that restriction of having to have a page file the size of RAM is now released. If you have a system with 8 gigabytes of physical memory, you may not have room for an 8 gigabyte page file. So that's a nice option in Windows 2000 to just record the kernel or OS and driver data structures, which often is really what you're interested in. You probably don't care about the process memory. It's more driver-related information you're looking at. So that's new in Windows 2000. When the system crashes, it doesn't actually write it to this file. It writes it to the paging file. And the reason for that is if the system is crashing, things are probably unhealthy enough that in order to be able to create a new file on the disk, you're asking too much of the system. You're assuming that too much is working. So it writes it to the paging file. The logon process then creates this crash system file on reboot, which is why it's not unusual to have a system running low on virtual memory when you reboot and log in. If the dump file hasn't been taken out of the paging file, your paging file has a whole bunch of itself that's still in use. So Given you've got one of these crash dump files, how do you get the crash code out? Well, there's some simple tools in the support debug directory. This is on NT4. On Windows 2000, it's in the resource kit, ResKit subfolder. And dump exam is the one that I'm referring to. Dump exam opens a crash dump file and produces a simple text report that, among other things, has the crash code. Look up the crash code in the NT Messages help file, or do a search in TechNet, and more than likely you're going to find some articles. Instructions on how to use dump exam for NT4 are in the Workstation Resource Guide. And I'm sorry I didn't find where the instructions are in the Windows 2000 Resource Kit yet. I looked last night and still wasn't able to find it. The other use of the debugging tools that we just referred to, one is looking at a static crash dump, is connecting to a live system. And this will be our last topic. We'll be done in about 3 minutes here. If you don't have enough disk space to take a dump, or you have a hung system, you have a system that's frozen or appears to be frozen, how do you break in and take a look around? It's fairly straightforward. There's a boot.ini option /debug, and the only way to add this is to manually edit boot.ini, that causes an NT system, without having to add any additional software, to load the kernel debugger client. By having the kernel debugger loaded, you have the option of breaking into what might be a hung system or appear to be a hung system. Now, I say appear to be because many times the system is in fact happily running something. It's just that the threads that handle UI input are lower than that something. So people say when the mouse doesn't move that the system is hung. It may be happily running something that's simply higher priority than the mouse input thread. Now, I have a 2000 machine here that I booted /debug, and that's all I had to do was add /debug into a boot.ini option. And I'm going to run the kernel debugger and break in. First, let's flip to that system on the right monitor. To enter. It was there? Oh, sorry. Try again. There we are. And I'm running this little app that's kind of in a loop here. I'm going to go to the debugging tools folder. This is Windows 2000. This is where the debug tools are installed, bin. Here's the kernel debugger. 2 environment variables need to be set, and these are on the slide. The location of the symbols, which in Windows 2000 is installed for you, and the baud rate. I chose a baud rate of 57.6. Debug baud rate. Now, before I do that, let's just take a look at my boot.ini on the other screen. And here's the second option I added. Actually, it's in the middle there. All I added was debug baud rate. I selected that option when I booted, and now I'm ready to break in. i386KD, run the kernel debugger. There's no indication that that we're actually set up properly until we break in. And to break in, Control-C. Watch what happens. System is hung, frozen, stopped. If I move the mouse, nothing. It's halted. And on the right, we have this little warning here. Now I'm going to flip back to the laptop here on the other screen. Come on. There we go. And it's kind of a dramatic notice. You are seeing this message because you pressed Control-C on your debugger machine's keyboard. Duh. This is not a bug or a system crash. If you didn't intend to break into the debugger, press G to go. But here I am in the kernel debugger with the system frozen, and I can go look around. I can look at the process list, or find out what the current process was, dump the driver database. Now I've got access to the 45 some odd kernel debugger commands that we're of course not talking about this morning, or this afternoon, but that are documented in the resource kit to some degree. But that's it for breaking into a hung system. I just wanted to demo that briefly. Just one other couple other points about debug. Why you don't want to boot production system /debug. you can't get it to take a crash dump. So if a system is hanging, you might want to boot it debug so that you did have the option to break in and poke around, but you're not going to want to run that on a production system. Crash debug does not allow you to break into a hung system, but does bring up the debugger if the system crashes. Why could that be useful? You don't have enough disk space for a crash dump. You want to be able to look around interactively when it crashes. Boot it / crash debug. When the system crashes, the debugger pops up. You can connect and poke around. Okay, I've gone over, so I'll leave you with these pointers to information sources. I'll be in the peer talk this evening for questions, or at the trade show during the trade show hours. Thanks for coming.
So she'll be down in show management office. Jenny, I'm sorry. No. We were just, I was just probably going to ask you whatever, say something. That's on the whole.
We got something special.